Today, we are on 5.1. So 5.1 is kind of an introduction into statistics and probability. So here we have a spinner with 12 equal slices. 4 are yellow, 3 are blue, and 5 are red. The dial is spun and stops on a slice at random. What is the probability that the dial stops on a yellow slice? So how would we represent that? Well, there are 1, 2, 3, 4 yellow slices. So 4 of the 12 would be yellow, and we write that as a fraction 4/12, which we would simplify to be 1/3. That means if lots of people play this game, 1/3 of them will land on yellow on their spin. Yeah. And the more you play, the more people that play, the closer the actual value is going to get to 1/3. Now, if 3 people spun it, does that guarantee that 1 will be yellow and the other 2 will not be yellow? No. Could they all be yellow? Right. Could they all not be yellow? Yes. So this 1/3 is what we expect to happen, but in practice, it's not going to be exactly 1/3. But the more times you play, the closer the value should be to 1/3. Okay. Same kind of idea here. A box is filled with 12 cards, or 12 brown cards, 3 blue and 3 green. What is the probability that a card being drawn is not blue? Well, how many cards are there total? There are 18. How many of them are blue? 3. So how many are not blue? 15. So the chance of drawing a not blue is 15 out of 18, which is going to simplify to 5/6. So 5 out of every 6 times you play this game, you should get a not blue. Now, that's not a guarantee, but that is what we expect to happen. All right, next question. A number cube with faces labeled from 1 to 6 will be rolled once. Why didn't they just call it a dice? Because some people think dice are evil. And technically, dice refers to multiple, and individually they are called die, but nobody calls them that, so I'm just going to call them dice. But technically, 1 is a die, and multiple are called dice. But, yeah. So, the number rolled will be recorded as the outcome. Give the sample space describing all possible outcomes. Then give all the outcomes of the event of rolling the number from 2 to 4. Now, this seems really, really simple, but we're going to be leading into more difficult sample spaces. So what are the possible outcomes when you roll a dice? 1, 2, 3, 4, 5, and 6. And you'll notice that these parentheses are these fancy wiggly parentheses. In mathematics, those denote what we call a set. So anytime you have multiple answers, then you can use those to say these are the answers. These are the possible answers. Okay? And what is the set of possibles rolling numbers 2 through 4? That would be the set. Wow, that was really pretty. 2, 3, and 4. So that was a really easy question, but it kind of gives you an idea of how sets work. Okay, a number cube is rolled 3 times. An outcome is represented by a string of the sort OEE, meaning an odd number on the first roll, an even number on the second roll, and an even number on the third roll. The 8 outcomes are listed in the table below. Note that each outcome has the same probability. For each of the 3 events in the table, check the outcomes that are contained in the event. Then, in the last column, enter the probability of the event. Okay? So, event A, an even number on the last roll. So how many of those have an even number on the last roll? Oop. This one, this one, this one, and that one. So how many of the events have an even number in the last roll? 4 out of 8, which becomes 1/2. Okay? Event B, an even number on the last roll or the second roll or both. So if there's an E in the middle or at the end, you win. So does the first one meet that qualification? Yes. The second one? Yes. The third one? No. The fourth one? Yes. 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 No. Yes. So 6 out of 8 becomes 3/4. Okay. See, an odd number on each of the first 2 rolls. The third one and the fourth one. That's it. So 2 out of 8 would be 1/4. Okay. Okay. A fair number cube is rolled. What are the odds in favor of rolling a 3? Okay, well, there's a difference between probability and odds. They are not the same thing. They're close, but they are not the same thing. Probability tells you the fraction or the percentage of something being likely to happen. So what would the probability of rolling a 3 be on a 6-sided dice? 1/6. Okay? But odds, instead of comparing how often something happens compared to how many options there are, the odds compare the probability, not the probability, the odds of something happening versus that thing not happening. So the probability is 1 in 6, but the odds are 1 to 5. Does that make sense? So it's the probability of winning compared to losing. I used probability again, sorry. Odds describe the chance of winning versus the chance of losing. The number of times you win versus the number of times you lose. Okay? And let's see if they give us a good explanation here. So the chance of winning can happen 1 time, and losing can happen 5 times. So the odds in favor are 1 to 5. What are the odds of losing? 5 to 1. Okay, let's do another one of those. A bag with 7 marbles is shown below. 3 blue, 1 yellow, 3 red. What are the odds in favor of choosing a blue? Well, 3 out of 7 are blue. But the odds would be 3 to 4. because there are 3 ways of winning and 4 ways of losing. So if you're hoping to draw a blue, what are the odds of losing? 4 to 3. Okay? Now, having said that, I want to show you guys something that I think you'll like. Let me pull this up. So you now understand odds. You guys have seen Star Wars, right? So, the Millennium Falcon has just gone into an asteroid field, and C-3PO, who is an android with a great calculator in his head, freaks out, and he says,
Sir, I noticed earlier the hyperdrive motivator has been damaged. It's impossible to go to light speed.
We're in trouble.
where is it?
No.
What are you doing? You're not actually going into an asteroid field.
They'd be crazy to follow us, wouldn't they?
You don't have to do this to impress me.
Sir, the possibility of successfully navigating an asteroid field is approximately 3,720 to 1.
Never tell.
What did he say? He said the probability of successfully navigating through an asteroid field is 3,760 to 1, which means you're almost guaranteed to make it through. Right? So he said the odds of successfully navigating is 3,760 to 1. So if you tried 3,761 times, only one time would you be unsuccessful. So when George Lucas wrote the script, he got it wrong. Right? He should have said, well, that's a good point. I think C-3PO was trying to say, this is very unlikely. But I guess we don't know. So what he should have said is, the chance of successfully navigating an asteroid field is 1 to 3,760. Or, what else could he have said? The probability, the odds of not navigating are 3,760 to 1. So in stats classes, that clip is like the example of a misuse of odds, and most stats teachers end up showing that. Okay, so don't be C-3PO. Don't say it backwards. Okay, a box has 4 cards, 1, 2, 3, and 4. Yolanda will toss a coin once and record the tosses as heads or tails. She will randomly pick a card from the box and record the number chosen. Give the sample space. Okay, so 4 cards, 1, 2, 3, and 4. Yolanda tosses a coin once and records the tosses as H or T. Then she will randomly pick a card from the box and record the number chosen. So what could happen playing this game? We could get H1, H2, H3, H4, or T1, T2, T3, and T4. Those are all possible outcomes. Does everybody understand? And a lot of times it's useful to write these out. Okay. So what are all possible events where the coin comes up as a T? It would be T1, T2, T3, and T4. So sample space is all of them. Those are all possible outcomes. And then the next question is just saying, what are all possible outcomes if you know that the coin was tails? The State Lottery Board is examining the machine that randomly picks the lottery numbers. On each trial, the machine outputs a ball with one of the digits 0 through 9. Then the ball is replaced in the machine. The lottery board tested the machine for 500 trials and got the following results. 0 happened 54 times. 1 happened 46 times. 2, 56, and so on. So, if we play this game 500 times, how many zeros would we expect? Well, 0 is how many of the total numbers? 1 in, well, there's 9 plus the 0, so 10. So 1/10 of the results should be a 0, which would be how many? What is 1/10 of 500? Would be 50. Okay? This is the expected probability. That's what should happen. Oh. Actually, they're not going to use expected. They're using theoretical. Sorry. So in theory, 50 out of 500 results should be 0. What about the number 1? How many times should the number 1 show up? The same. 50 out of 500. Okay? So that is the theoretical. Monty, what are you doing? You're doing her assignment. Hannah, do your own work. Uh-huh. So the theory says 50 out of 500 should happen. Okay? But what did happen? Well, with the 0, we ended up with 54. Does that mean the machine's broken? That's pretty close, right? What if we ended up with 3 zeros? Would you be worried that the machine is broken? What if we ended up with 400 zeros? Would you think the machine is broken? Yeah, but 54? That's pretty close. Okay? So, what is the experimental probability of getting either a 2 or a 4? So 2s happened 56 times, and 4s happened 45 times. So if you add those together, you're going to get 101 out of 500. Okay? So when we did this experiment to test the lottery machine, we ended up with 101 out of 500. Okay? What should have happened? What's the theoretical probability? If the machine is fair, what should happen when we count 2s and 4s? We expect 100 out of 500. Now they're not equal. Does that mean the machine's broken? No. Right? It's not going to be perfect. Could it be perfect? Sure. Will it be perfect? Probably not. Now, one thing that you learn in statistics the further you go, and we won't be dealing with it in this class, is how far is too far? At what point do you say the machine's broken? If you had 110, would you say the machine's broken? Probably not. 120? Maybe. 200? Probably. 300? Definitely. Right? So where do we say, if you step over this line, then we're going to say that the machine is broken? And the answer is wherever you want. Right? Brooklyn might say, when you get to 130, the machine is broken. And Cadence might say, no, when you get to 145, the machine's broken. And there really is no definite line. You have to pick the line, which is a little bit scary, but that's how it works. All right. Assuming that the machine is fair, choose the statement below that is true. With a large number, with a large number of trials, there might be a difference between the experimental and theoretical probabilities, but the difference should be small. If we play this game a long time, will the theory and the experience be equal? No, but they should be close. So that one could be true. With a large number of trials, there must be no difference between the experimental and theoretical probabilities. If we play this game a lot of times, does that guarantee that the experimental and the theoretical will be equal? No. With a large number of trials, there must be a large difference between the experimental and theoretical probabilities. No. The more times you play, the closer they should be. So the answer is the first one. An ordinary fair die is a cube with the numbers 1 through 6 on the sides, represented by painted spots. Imagine that such a die is rolled twice in succession and that the face values of the two rolls are added together. This sum is recorded as the outcome of a single trial of a random experiment. So we're rolling a dice twice. Compute the probability that the sum is greater than 8. So what could happen? If we roll a dice 2 times, what could happen? Well, let's write them all down. What are they? So 1, 1, because we're rolling it twice. What else could happen? 2, 2. I'm going to put that here. So let's do all of the ones that start with 1. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. What else could happen? 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 6, 5, 7, 5, 8. Oh no, sorry. 6, 1. I don't know. That was weird. I just kept counting. 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So how many possible outcomes are there? 6 rows, 6 columns, 36. Okay. So how many of them have a sum greater than 8? So does 8 count? No. So we have to go greater than 8. So any number that adds together to be greater than 8. So, oh, I missed this one, those 2, those 3. Wait. Oh, that's a 5. Okay, that was, and then those. So 4, 5, 6, 7, 8, 9, 10. So 10, the probability of getting a sum greater than 8 would be 10 out of 36, which is 5/18. Okay, what about the sum being an even number? So let's count all of the ones where the sum is an even number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 out of 36 would be 1/2. So half of the results are even and half of the results are odd. So this is where writing out the sample space comes in handy. You write down every possibility and then you just count the ones that you're looking for. Oh, that's it. Okay, get to work.